Hello and welcome to R4 Psychology. I'm Dr. Andy Hales at the University of Mississippi, and in this video we're going to look at how to perform an independent samples t-test in R. So the goal here is to take two different groups and conduct an analysis where we test whether they're significantly different from each other. We're going to use the tidyverse and effect size packages from last time, and also ggb swarm for one of the figures we're making here, so load those up. And we'll also use the same data set, and to simplify things, I'm selecting just the handful of variables we're going to need. All you really need to do an independent samples t-test are two variables. For good measure, I kept in participant number just because that's nice to have for organization. But what really matters is we've got an independent categorical variable with two levels. So here we ask people whether they self-identify as more of a cat person or more of a dog person. So our first participant here is a cat person, the next several are dog people. And for each of them as the dependent variable, we ask them to estimate the number of Skittles that are in a regular sized bag. So our first person thought there were 36, our next thought there were 33, and so on all the way down. Now the question here is, do we have evidence for a significant or a systematic difference on average between the estimates issued by cat people versus dog people? Now, this is a cartoon example to illustrate how a t-test works. But I don't know, you could imagine someone building a hypothesis around this. It might be far-fetched, but you could theorize that dog people are optimists and they have an abundance mindset, and they might be inclined to think there are many, many Skittles, whereas cat people are maybe more conservative. Who knows? Let's do a t-test. Let's find out. Now, before we go in and start computing p-values like maniacs, let's do some basic descriptive analysis first to make sure we understand our data. For starters, we've got this independent variable. Let's make sure we have a reasonable number of people in each group, right? If we only had 2 cat people and 45 dog people, then that would be so imbalanced we'd be concerned. Let's look at the frequencies then. We can use the table function from earlier when we were doing descriptive statistics, and we can see we have 20 people self-identified as cat people, 28 self-identified as dog people, and we have one person who apparently didn't give an answer to that question. Now, of course, we won't be able to use them as part of the t-test because we don't know which group they're in, so I'm going to go ahead and simplify things by removing this case, and we would simply make a note of that and report it as necessary and proceed with the analysis with the cases that we do have. So let's take a look now at our dependent variable and see what sorts of averages we're working with. To generate the means and standard deviations for each group, we can use this tidyverse syntax where we group by our categorical variable and then compute the means and standard deviations. And we can see on average, cat people are estimating 49 Skittles, and on average, dog people are estimating 44 Skittles. But notice these standard deviations are pretty large. We got a lot of variability here. Tables are great, but there is no substitute for just laying eyes on your own data. And a really handy way to display this sort of data is with something like a scatter plot, where we can actually see the individual data points, and bee swarms that jitter them intelligently are a really nice way to look at these. So without getting into the R code, you could update the variable names here as needed, but this code produces a plot that gives us a pretty reasonable overview of the distribution in each group, and also the mean level in each group. So the height of the bars here indicate the average. And you can see it looks like cat people maybe have a slightly higher average than the dog people. You'll notice we also have these error bars around each group. If you look at the code, for this particular graph, I've set it up so that these error bars are mean_SE. So that would be the standard error of the mean in each group. And that's always a very useful thing to put on figures. Sometimes you might put the 95% confidence interval of the mean in each group. Nothing wrong with that either. Whichever one you go with, always a good idea to clarify that in the figure note so that people know which error bars they're looking at here. So we can see our distributions, we can see the standard error for each group. let's go ahead and actually conduct our t-test. Now, to do that, we're going to use the same t.test function from last time. We're just going to change the information that we give it. So here, we're going to use what's called formula notation and tell it that our dependent variable is estimate, and we're essentially going to be predicting this dependent variable from our independent variable of dog cat, whether people said they were a dog or a cat person. And we need to tell it the name of our data set, which in this case, coincidentally, is called data. So it looks redundant here, data equals data, but that's just because our data frame here is named data. And when we run this, we get our t-test. Now, R by default gives you the Welch's corrected degrees of freedom. So here we have the Welch two-sample t-test. So right off the bat, we get our t value. We see here it's 1.15. Our degrees of freedom, they have decimals. They're supposed to because it's a Welch's corrected degrees of freedom. And our p-value in this case is 2.55. We also have a restatement of our alternative hypothesis. Again, two-tailed test, so that looks the way it should. And we have a 95% confidence interval around the raw mean difference. So in this case, our 95% confidence interval is estimating that on the lowest possible end, the difference between these two means in the population could be as low as 4 Skittles, or on the high end, it could be as large as 16 Skittles. Now, something to notice here is that the value of 0, a difference of 0, meaning cat and dog people estimate identical numbers of Skittles, that fits comfortably within this interval. That's exactly what you would expect when you have a hypothesis test that is non-significant. Finally, the test just restates for us the mean of each group, which we computed for ourselves above. Cool. All right, so we've got an independent samples t-test here. Now, there are good reasons to default to the Welch's correction for t-tests, but there may also be times when you'd prefer to report a pooled variance t-test where you don't correct the degrees of freedom, and instead, as the denominator in the t-test, you use the pooled variance term. And if you'd like that, it's easy enough to request. You just add in the argument var.equal to indicate that you'd like it to treat it, each group as having equal variance, and you set that to true. And when you do that, you get a similar but different t-test. This is just a good old-fashioned two-sample t-test, and here you'll notice the degrees of freedom is 46. This time there are no decimals in the degrees of freedom because we're no longer using Welch's correction. Also, the t-value is computed slightly differently because it's using the pooled variance term. However, in this case, the effect on the p-value was pretty negligible, and the results down here are also updated accordingly. Of course, the means in each group are going to be the same either way. So that's how you compute the t-test. As always, it's wise to keep an eye on effect size and report that alongside any hypothesis test that you report. And again, we can do this in two different ways. We can look at the unstandardized effect size. Here it would be the difference in numbers of Skittles, or we can standardize it as Cohen's d. So starting with the unstandardized effect size, we can simply use dplyr data processing here to group by our independent variable and compute the mean for each group, and then calculate the raw difference between them. This is basic arithmetic. You could do it by yourself. The nice thing about using code here is if someone comes along and runs another study and they have a new data set and they want to use the same code, well, then here you don't have to manually override numbers. You punch it in yourself. So that's why it's always nice to use code when you can. And in this case, we can see that cat people, on average, estimated 5.84 more Skittles than dog people. Or I guess to phrase that more logically, we'd say dog people estimated 5.84 fewer Skittles than cat people. That's not a lot of Skittles, but we shouldn't be shocked. We don't have a gigantic sample here, and the test didn't show any evidence that this is different than what we would expect by chance. So the effect size doesn't seem huge. And if we wanted to express this in standardized units of Cohen's d in standard deviations, We could use Cohen.d. This is a function from the fsize package, and we give it the same information as our t-test above. We tell it the formula we used and the name of our data frame, and here it expresses that mean difference, but this time in units of Cohen's d or standard deviation. So here it says the Cohen's d estimate is 0.34. Now you'll recall from earlier, it unhelpfully likes to editorialize and give us its opinion about whether this is a small effect size or a large or a medium effect size. Here it happens to think this is a small effect size. Again, it's not up to the package whether this is a small effect size or not. That's up to the researcher's interpretation, and you may have to make a judgment. You might have to argue for why an effect size is small or large in a given context. There's no one-size-fits-all formula here. And in fact, I find it a little irritating that 0.34 is dismissed as small, because there's good reason to think from meta-analyses that in social psychology, at least, most effect sizes are actually right around 0.34. So I don't think this is an atypically small effect size, even if with this small sample it didn't happen to be flagged as significant. That doesn't mean that overall 0.34 is small. Maybe it is, maybe it isn't, depends on what you're studying. And again, we have a 95% confidence interval around the standardized Cohen's d that also includes 0. And again, this lower and upper bound, it's no longer in raw units. According to these calculations here, it's in standardized Cohen's d units. So there you have it. That is how you perform and interpret an independent samples t-test in R. See you next time.